Okay. Can you hear me in the back? Can you hear me? Good. Okay. Couple quick surveys. How many of you have finished MP2? Okay, very good, very good. For those of you who are wondering how the exams are going to work out, this is a good time to start thinking about the exam, especially when you work on the MPs and begin to think about how you study the exam for the exam. So in the class schedule, we have posted last semester's exam and also the study guide. This is the study guide from fall of 2017. It's still very, very relevant, okay? And we're going to probably update it just a little bit, but not a whole lot. So this was something that we started to do, started doing last semester, and people really found it very useful. So as you begin to finish up your MPs and finish up your questions, this is actually a good next step for you to go and see, okay, what are the variations and what are the typical things that we want you to really master, and use that as a study guide. Work out some of the questions, even try to do some of the programming yourself, because some of these things are alternative implementations of MPs. So you can even try some of these alternatives. Okay, and these things can really help you to do very, very well in the exams. Okay, so you have plenty of time. You don't have to panic about exam today. Okay, there's something wrong if you start to panic about the exam. Come and talk to me. There shouldn't be this much stress. But you really can do yourself a big favor by keeping up with the MPs and use the study guide along the way. Okay, to make sure that all these concepts are really solid as you go. Okay, we have quite a bit of work to do today, but also I want to make sure that I announce this. On Thursday, I'm going to be lecturing from Chicago. So this is the first time you're going to be seeing the streaming video, and we're going to work with IT to make sure that that session goes smoothly. But I also like to get your feedback about how it worked out. And is there anything we can do to make things better when we stream from Chicago? Okay, let's go and talk about locality and tile matrix multiplication. So today we're going to learn about how we can evaluate the performance and learn about the concept of tiling, and we're going to prepare you for MP3. Tiling is one of the very fundamental techniques for high-performance computing. I would equate that with leverage in human civilization. Okay, and if we don't have leverage, we wouldn't be able to move big objects and make things work with our limited physical strength. And tiling is really a very similar technique. We have very limited amount of memory, and we use that as a leverage so that we can process data at a much faster rate than what we could without. Okay, so that's how important it is. And it's really the staple of high-performance computing, whether you're in the CPU domain, in the GPU domain, or in anything that with performance. So here is the kernel invocation that we talked about last time. So we have a tile matrix multiplication. And then, we have these, not tile matrix, basic matrix multiplication, and we use a, simple third block structure where we essentially have tile width by tile width threads in each thread block. So we launch the kernel, and here is the kernel. Here's the kernel code of the basic matrix multiplication. And I'm not going to go through that again, but there's one important thing I want to make sure that you really see. If you look at the for loop in the kernel, in the for loop, we have a multiplication, a star sign, right? That's a multiplication. And then we have an add accumulate into the p-value, right? That's the add equal sign. So we have two operations, multiply and add. In order to do this statement, we need to fetch m element and n element. So we're doing two memory accesses into the global memory, one for m element, one for n element. And then we do a multiply and add. So we're doing two global memory accesses and two floating point arithmetic operations. So the ratio between floating point operations and memory access is 1 to 1. Okay? On average, we do one memory access for each arithmetic operation we perform. So this is a very important ratio, and we call it the compute to memory access ratio. 1 to 1 is a very low ratio, but unfortunately, for most of the code that you're going to have, if you write a naive piece of code, you're going to get this ratio. It's going to be close to 1 to 1. And so this leads us to the slide that we ended our last lecture, where we say, in order to do one floating point operation, we're going to have to access one global memory operand. So the best we can do in terms of computation is the fastest way we can fetch these operands from the memory. If we try to do any faster computation than the speed at which we can fetch operands from memory, the memory system is not going to keep up with us. So we would be waiting for the memory. Okay? So the fastest execution rate that we can sustain is the rate at which, for this kernel, is the rate at which the operands can come into the processor. And each operand is 4 bytes, right? Each operand is 4 bytes. So for a processor with 150 gigabyte per second memory bandwidth, the fastest rate at which the operands can come into the processor is 150 gigabytes divided by 4, which is 37.5 giga-operands, right? Every operand is 4 bytes. So the fastest rate that you can move the operands into the processor is going to be 37.5 giga-operands per second. And that's the fastest rate you can do the floating point operation, because for every floating point operation, you need to have one operand, right? It's the two operations for the two operands. So 1, 1. And that gives you the upper bound of how fast this processor can run for that piece of code, okay? And if you measure the real hardware execution, you just run that piece of code on something like the Fermi processor or Maxwell processor with this kind of characteristic, you're going to get a little bit less than that upper bound. The upper bound, 37.5, is assuming that everything else works perfectly. You're only limited by the memory access. But in reality, you have a little bit the overhead here and there, kernel launch, thread management, and then you have a little bit of overhead, and things may not work exactly right in the microarchitecture, so you get about 25 giga operations per second. And we mentioned that for a typical processor that can have 150 gigabyte per second memory bandwidth, you will have definitely more than 1 teraflops of compute power. So that will give you only less than 3%, okay? And typically about 1 to 2% of your capability, that is the peak, what we call the peak performance execution rate for this processor, is over 1 teraflops, or 1,000 gigaflops. But with that piece of code, you will be only using about 25 gigaflops, and that's 2.5% or less. Okay, so that's why it's kind of a very, very basic piece of code, and you're using a GPU, you're doing okay, and in fact, if you look at a typical CPU in that same generation will be executing probably slightly less than 25 gigaflops. So even a very basic piece of code will be executing probably faster than a sequential code on the CPU anyway, right? But that's a good start, but it definitely is not where we want these processors to be when we build the teraflops compute capability into the processor. Today, we have a new processor, Volta, and the Volta processor has almost 10 times. Okay, so if we look at the memory bandwidth, it has increased about 6 times. So if we increase from 150 gigabyte per second to 900 gigabyte per second, they say, whoa, you know what? These guys are doing a great job, right? From Maxwell to Kepler, Kepler to Maxwell to Pascal to Volta, they increased the memory bandwidth by 6 times, which is great. But if you look at the compute throughput increased even more. Right now, the compute throughput of the Volta processor is close to 15 teraflops, right? So you see the technology advancement. You still see that huge ratio between what the internal capability is versus the external bandwidth. So that's why when I introduced the introduction slide about memory bandwidth, this is what I want you to remember. It's not a reservoir. You open up the floodgate and the data just gush out. It's more like you're really, really thirsty, and then you have a very, very narrow straw, and you're trying to suck as much liquid as possible into, from the glass. And that's really a good illustration of how starved the processor can be executing these kind of basic algorithms. Okay, so we're going to do a whole lot better, and this is the beginning of how we can do a whole lot better. So we're going to do tiled matrix multiplication using shared memory. We talked briefly about shared memory. We haven't really talked about exactly how to use it, and so this is the lecture that we're going to begin to delve into it. So we're going to start by talking about tiling as a general programming methodology. Tiling is used extensively in CPU libraries, even in sequential code. Intel math kernel library used tiling extensively. And if you look at a piece of code in Intel MKL math kernel library, you will see that oftentimes you would expect a piece of code to be maybe 20 lines of code, doing something like a simple matrix multiplication. In fact, I show you that sequential piece of code. That's a very small piece of code that you can write for matrix multiplication. But if you look at the real Intel math kernel library code, the matrix multiplication code is literally thousands and thousands of lines of code. And a good part of that is the various forms of tiling that they implemented for different shapes of matrices, for different kinds of alignment, situations, and so on. And we're going to actually see some of that in our tiling, in our tiling section. And so you will begin to see that there are only a few number of techniques that people use all the time, whether it's in sequential programming, in parallel programming. And so here, my job is to introduce tiling in the context of parallel programming. Okay. So we start with the global memory. We were accessing M and N from the global memory. And the global memory is implemented with DRAM, dynamic random access memory, and they're slow. They're very, very slow compared to the processor. So a profitable way of performing computation on the device is to tile the input data. So a very good example here, you look at this piece of wall, and the wall is big, but then we have these tiles, right? The wall is built with these tiles. So if you need to clean the wall, you can try to clean the wall in any way you like, or you can just kind of take one tile at a time and then just clean each tile, and then go down the row. So this is not that different from how we're going to do computation with tiling. Okay, we're going to divide up the surface or the volume into these chunks, and then we're going to process one at a time until we're done, and then we'll assign these tiles to parallel thread blocks, And each thread block will probably process one of these tiles, and we really make great use of on-chip memory when we process that tile. We're going to avoid doing any unnecessary global memory accesses as possible in that, when we process each tile. So we partition data into subsets that fit into the smaller but faster shared memory, and we handle each data subset with one thread block. So every one of these tiles will be assigned to a thread block, and so the thread block has a large number of threads, right? A fairly large number of threads. So the threads will load the tile, the data in the tile collaboratively. So we want to make use of parallelism when we load data into the shared memory. So all the threads will contribute and load the data from global memory into the shared memory. And we perform the computation on the subset. So everyone help to fetch the data into the shared memory. And then everyone enjoy accessing the shared memory, which is much faster than the global memory. And then, by the time you're done with the data, you can, you write your result into the global memory, and you're done. Okay, so this is a very, very basic but very common pattern of computation when we use tiling. Tiles are also called blocks in the literature. So tiling and blocking oftentimes are used interchangeably in the literature. But here, because we have thread blocks, we try to use only tiling, not blocking, just to avoid some confusion. So, but if you hear people saying that, hey, I'm doing tiling for my cache, I'm doing tiling for my, locality, that means tiling, blocking and tiling mean the same thing in that context. Yes?
So is the shared memory sort of like a cache?
So the question is the shared memory sort of like a cache? The shared memory is what we call the programmer-managed cache or scratchpad memory. Cache memory in general is transparent. So in the CPU, when you access data, sometimes that data gets into the cache. It's up to the hardware to decide whether the data gets into the cache. So you don't really try to move data in and out of the cache, but according to your access pattern, the hardware has policies for replacing data and putting data into the cache. Shared memory is visible to the programmer, and you explicitly move data in and out of the shared memory. So you're going to see that code, and that's why in the CPU world we usually call this scratchpad memory. Question here.
If there's some concept similar to like prefetch.
Okay, so the question is, how is this related to prefetch? Prefetch in the CPU world means that before you need to use the data, you have, ahead of time, you go and touch that data in the cache or in the memory, so that you trigger a cache fetch access sequence long before you try to use the data. So in 4.11, you actually have stranded prefetch kind of things that for extra credit if you are taking 4.11. The shared memory loading is not exactly prefetch, because you are actually, the prefetch is usually a prediction of, maybe you need this, so you go and touch it, and so you get the data in. And fetching into or loading into the global memory is deterministic. The programmer says, I need that data, load that data now, and I can use it. Having said all that, the effect is actually quite similar, because what really happens in the prefetch, actually I'm going to come back to this point, because of the zero cost scheduling and latency tolerance, you will get similar effect to the CPU prefetch by loading into shared memory. Okay. So here let's start with how we're going to approach, how exactly are we going to use the shared memory, and then how the tile would work exactly. So in order to use shared memory in a kernel, you need to declare variables or arrays into the shared memory. Okay. So here we're going to have a small tile of m and a small tile of n that we want to load into the shared memory for a thread block. So inside the kernel, we're going to have this underscore underscore shared underscore underscore keyword. Remember, I actually showed you that table a couple lectures ago for exactly this reason. When you declare an array in the kernel, inside the kernel with the keyword shared, that means that the kernel will be able to access a piece of shared memory array. And this array is going to be per thread block, meaning that every thread block will have its own private version. So when you launch the kernel, you're going to have a grid, and then you're going to have all the thread blocks. Every thread block will bring up will have its own shared memory subtile M and subtile N in this case. And all the threads in a thread block will see the same contents of those two arrays, but all the threads in another thread block will see a different subtile M and subtile N. So the number of shared memory arrays allocated to this entire grid is going to be the number of thread blocks, right? So you're going to be allocating one array, subtile M array and subtile N array for every thread block. And if you have 1,000 thread blocks, you're going to have 1,000 different versions of these arrays, okay? The number of different versions will be this number of thread blocks. So how do we actually do the computation? The basic idea is actually quite simple. So you have these threads. And for matrix multiplication, you have every thread producing one output element, right? That basic matrix multiplication, we're using every thread to produce one output element. And the one output element is produced by accessing one row of M and one column of N, right? So you can think about it as threads, and each thread is going to be making lots and lots of accesses into the input data, right? Each thread is going to be accessing one row of M and one column of N. Thread 1, thread 2, they're going to be all accessing multiple data elements. So if we don't impose any kind of discipline in the access timing, then thread 1 can be accessing its data in arbitrary ways. Thread 2 can be accessing data in arbitrary ways. They may or may not be accessing the same location, and so they can do anything they like. So in tiling, what we do is that we impose a discipline. We actually impose a discipline about how and when these accesses are done. So we're going to say, thread 1, in this time period, you can only access a subset of the data, okay? You have to only access that subset of data during this time period. Thread 2, you can also only access this subset of data during the same period. So we make sure that these threads are operating in similar time schedule so that we can load that subset of the data into the shared memory and have all the threads involved to be able to access that subset from the shared memory. So if we didn't have that discipline, and whether thread 1 wants to access a particular subset, thread 2 wants to access another different subset, then there's no way they can both access the shared memory because they need to have different subsets of the data. We force them to have similar execution schedule so that they can collaborate, they can use the data in the shared memory without going out to the global memory. Okay, so that discipline is going to be extremely important, and we enforce that discipline with the mechanism called barrier synchronization. Okay, so how do we do this? We identify a tile of global data that are accessed by multiple threads. Okay, you have to figure out what kind of subset are being shared across threads, and then you load the tile from that global memory, into the on-chip memory, And then we have the multiple threads to access their data from that on-chip memory. And then we move on to the next tile or next block. So let's take a look at matrix multiplication. So we have talked about these abstract concepts. So let's zoom into the matrix multiplication and see where this kind of sharing behavior really comes in. So remember, when we do the matrix multiplication, where each element is in the product of one row of n and one column of n. So let's take a look at these two output data elements in the same column, right? P, these two P elements in the same column here. These two are in the same column. That means that they're going to be produced by a row of m and the column of n, and that column of n is going to be common to these two elements. So the threads, the two threads that are producing these two elements will both want to access the same column of n. That's where the sharing comes in. Those two threads will be sharing access data, right, for that column. So if we load elements from that column into the shared memory, then both threads can access that data from the shared memory rather than individually going out to the global memory and access that data. Okay? So if we load each element into the shared memory, we will have several threads use the local version to reduce the memory bandwidth. And you can imagine the same thing in terms of rows. I can easily have two data elements in this row, then that will be accessed by the same the same row will be used to produce these two elements, but two different columns will be used to produce those two elements. So let's say if I have a thread block of 16 by 16, and every thread is going to produce one output element, right? That's how we design the basic matrix multiplication code. What that means is that every row, every column here is going to be used by 16 of these output elements, right? And every row here is going to be used by 16 of those output elements in the row. So if you look at it carefully, you will see that for a 16 by 16 thread block and 16 by 16 output tile, we call this output tile because it's a tile of output elements, every input element m and input element n used in that process will be used 16 times. So if you have a square tile of tile width, then every input element will be used by tile width times. It could be from the reuse in the m will be reused by multiple columns of n, and then n will be used by multiple rows of m when you produce the output, right? So m and n, each element will be reused tile width n time, tile width times. And so that's why we're going to try to use as big a tile as possible, because the size of the tile will determine the actual reuse and actual benefit of tiling. And at the end of the lecture, I'll give you a simple calculation, and you will see exactly how it works. So how do we do tile multiply? The way we do tile multiply is by break up the execution kernel into phases. Remember that discipline? Remember that discipline that I talked about? This is where I'm going to begin to impose discipline. I'm not going to just let every thread to go all the way from beginning to end, for that inner product, okay? That's wild. So what I'm going to do is I'm going to divide up the inner product into sections, into phases, okay? Each phase is going to have a small part of the inner product. So let's say if I have, tile width by tile width output tile, then I'm going to just allow the inner product to progress by tile width steps, okay, in each phase. So let's say if I have 1,024 by 1,024 matrices in my matrix multiplication, and I'm using 16 by 16 tiles, okay, output tiles. Then I'm also going to only allow every thread to do 16 steps, okay, 16 steps of the inner product in each phase. So I would need to have, the 64 phases in order to complete a inner product for a 1000 by 24 by 1024 matrix. Okay, so these are the kind of the numbers that you should be playing with, so that you can have you can be very, very comfortable with this kind of algorithm. So every phase will be a small section of the inner product. So what does it mean in this picture here? When I produce this element, I'm going to need to have this row of m and this column of n. And in each phase, I'm only going to allow the inner product to progress by having this small segment of m and small segment of n for the inner product. So that's what I was talking about. If I have a tile width by tile width output tile, I'm going to only allow tile width number of steps in each phase. So when I impose this kind of discipline, then what I can do is I can load up a tile of m, blue here, and tile of n, blue here, and then I can allow every element, meaning every thread, right, every thread in the thread block, to perform its phase of the matrix multiplication. This one is going to be this by this, and this guy here is going to be this by a different section of the row, from a different row, right? So everyone can do its phase, okay, it can do its phase once we loaded the tile m and tile n into the shared memory. So how do we load it? This is actually one of the most challenging part of tiling. How do you calculate the tiling index when you load the m tile and n tile from global memory into the shared memory? So you have to make sure that you really understand the conceptual design, and then you go, then the code will make perfect sense. So we want to make all the threads in a block to participate in the loading, okay? And everyone share the burden. So each thread loads one m element and one n element in the basic tiling code. And then we assign the loaded element to each thread such that access within each warp is coalesced. I'm talking about this term without really defining the term yet. So, but I want you to just kind of remember the word coalesce for the moment, okay? And then I'm going to come back and give you quite a bit of treatment on that concept. So what we're going to do is we're going to essentially go back to here. Look at the output tile. The output tile is that yellow. And so because we're using square tiles, and we're using the same width, the number of steps in each phase as the tile width, we can literally just load the same size and shape of input tiles. Look at those two blue ones. They're exactly the same size and shape as the output tile. Okay? If you have a squared tile, if you have a rectangular tile design, then it's different. Okay? People do use rectangular tiles, but it's quite a bit more complicated, and you will need to redesign your indexing. So it's actually one thing that you should play with, but for the lecture, I'm going to stay with square tiles. And for most of the class, we're going to also stay with square tiles. It's different than rectangular matrices. In the MP2, MP3, you need to be able to process rectangular matrices, but we're still using square tiles for simplicity, just to make things simple for you. But for those of you who really would like to understand more about these things, you should be playing with rectangular tiles as well. So now that we have exactly the same shape and size of input tiles as output tiles, what we can do is we can just assign all the threads to load the input tiles exactly the same way as they produce the output tile elements. So here, thread 0, 0 is going to produce P0, 0. Thread 1, 0, 1 is going to produce P0, 1, and so on. So we use exactly the same assignment as when we load the M tile and N tile into the shared memory. So we will have thread 0, 0 to load M0, 0, thread 0, 1 to load M0, 1, and so on. So we assign the threads to load exactly the relative locations of M the way that we assign them to produce the element of P. Same thing with N. So we're going to have thread 0, 0 to load N0, 0, thread 0, 1 to load N0, 1, and so on. So if you keep this conceptual picture clear, you're going to be able to see exactly how the code should work, and you will be able to produce the indices in exactly the right way. If you did not have this conceptual picture in mind, that code is going to look like garbage. Okay, the code is going to look just like noise, and many people looking at the tiling code, most engineers cannot understand tiling code because they never understood the underlying engineering design of the loading process and so on. So let's. So this is the work for block 0, 0. We have a small matrix example here, 16 elements, 4 by 4. We're going to use 4 thread blocks to process to generate the product P matrix, and block 0, 0 will generate these 4 elements. So we will go in order to generate these 4 elements, we're going to need to access M, row 0 and row 1 of M, and column 0 and column 1 of N in order to produce all the inner products for this value. We're going to impose the discipline by dividing up the inner product into these phases. So we're going to divide the inner product into 2 phases in this example, right? It's the ratio between the matrix size and the tile size. So that's ratio of 2. So we're going to divide up the inner product into 2 phases. During phase 0, we're going to load this input tile, which is exactly the same size as the output tile, and this input tile N into the shared memory. So this is the shared memory M subtile, and this is the shared memory N subtile. And every thread is assigned to load 1 element. So these are the loading of the 4 threads, okay, into the shared memory. And here for N, we have the same thing. We have the 4 threads, each loading 1 N element. So once we loaded that tile, all the threads are now going to just use the shared memory data for the inner product. Each of them are going to be doing 2 inner product steps. Okay, 2 inner product steps from the shared memory. So thread 0, 0 is going to use M0, 0, N0, 0 for the first product, and then M0, 1 and N1, 0 for the second multiplication, and then it accumulates into that section of the inner product. So after this point, the P elements now have a partial inner product, right? That incorporate 1 phase, okay, 1 phase worth of the M and N elements. So this is the second step for all the second step of all the threads. Once we're done with that first phase, all the threads go back and load the next tile, right? Now they're ready for the next phase. So all the 4 threads are going to go to this section, which is the next tile for producing these P elements. So again, each of them will load 1 element of M and 1 element of N, and then they go into the compute. They're going to access each thread is going to be accessing their first M and N elements worth in the tile, and then the second step. So once we're done with that second phase for that small example, all the P elements are complete. And you can write the P elements into the global memory. Okay, and then the thread block finishes. Okay, that's all thread block 0, 0 need to do. So let's take a look at how we can load these elements for input tile 0 for thread block 0, 0. Yes? Question?
So I understand like what you're saying here, but the
Yeah.
question I have is how is it faster given that we have to do more memory writes because of the thread blocks having to write to the same?
Yeah. Excellent question. So the question is, you know what, it looks like we'll be doing more memory writes to P, right? So is that one of the, right? So the answer is actually we don't. So the threads actually just accumulate those P values in the register. And at the end, they will write out into the memory. And when we show the final code, you will see that we're accumulating into this local variable, which is a per thread register. And in the end, we'll just write it out.
And so does each thread still correspond to one output?
Yes. Yeah. So that's the invariance between the basic code and the tiling code. In reality, both the basic code and tiling code can process multiple elements. Okay. But they don't have to be different. They can both process one output element. They can both generate multiple output elements. But when I show you these examples, I keep that as invariant. Whatever the basic code does, the output, the tile code also will do that. Okay. So let's say we're loading. How do we load input tile 0? So this is that phase 0. Okay. We're going to be loading M and N, the two blue tiles into the shared memory. So if we look at the positioning, remember we're going to have the threads, all the threads to load the inputs in exactly the same relative assignment as the way they generate P. So if I'm generating output element here, P element here, I'm going to be loading the M element in the same relative position and the N element in the same relative position. So another way of looking at it is that when I load an M element, I'm going to be loading from the same row as the output element that I'm going to be generating. Okay? So I'm going to be loading the same row, but the number, however, when it comes to the column, I'm going to be using my thread index X to find where I'm supposed to load, just as in the output tile, I'm using the thread index X to write to the right P element. So I'm going to be using row as my row index, the row variable as my row index, and TX as my column index. When I load the tile 0, of M. When I look at N, it's a little bit different. When I look at N, the same exact position, but the number of columns that I need to go, I need to actually go to the right column of N in order to find the element I'm going to load, and that's in my column variable. So because this column variable gives me the column position of my output, which is also the column position of the element I'm going to load. And then, but for Y, I'm going to just go down by thread index Y, okay, so that I can find the correct element. So these two are the values, the variables I'm going to use in order to find the M element and the N element that I'm going to load as a thread. I'm going to load from the global memory. But that only works for tile 0, okay, for tile 0 or phase 0, okay? Now, when I go in and load the orange tiles, tile 1 for both, for both M and N, I'm actually going to be progressing, right? I'm going to be progressing in the M matrix and N matrix. I'm moving horizontally by one step, right? I'm moving horizontally by one tile width in the M tile and moving vertically by 1 tile width, right, to find the tiles, the second tile 1 for M and N. So the way that I make that move is that I will stay in the same row. For M, I'm staying in the same row, right? I'm still staying in the same row, so it's still the row variable here. But then, instead of just using Tx as I had in, in tile 0, I'm going to add tile width, 1 tile width to my original column position to move that into the tile 1 column position. For N, it's the vertical version. So I'm going to be staying in the same column. Okay, I'm going to be staying in the same column, but as far as rows are concerned, I'm going to be moved down by 1 times tile width number of rows to move to the next element I'm going to load. So that's why for the row index, I'm going to add tile width to ty, and then I'm going to use the same column. Okay, so let's begin to generalize into variables. So let's say we use an M variable, which is a loop iterative variable for the number of faces. Okay, M is going to go from 0 to whatever number faces we have, and M is 0 for phase 0 and 1 for phase 1. So when I use M as a loop variable for every thread to progress from phase 0 to phase 1 to phase 2, M is going to be going from 0 to 1 to 2 and so on. So then for the M element that I'm going to load, I'm going to use all the M elements that the thread is going to load will remain in the same row. So that same row is going to be used for the row index. But then for column index, it's going to be moving from Tx to 1 times tile width plus Tx, 2 times tile width plus Tx, and so on. So that's M times tile width. For N, it's the vertical version. So all the elements to be loaded by a thread will use the same column index. But for the row index, it will go down from Ty to 1 times tile width plus Ty, 2 times tile width plus Ty, and so on. So that's M times tile width plus Ty. So those are the indices that you're going to see in the code. Okay? And we're going to see a for loop. We're going to see the for loop incrementing M, and M is going to be used in the indexing for M and N. But it's very, very important, I'm saying this the third time, that you remember you are loading these blue, orange tiles. One go from the horizontal direction, one go from the vertical direction. And within each tile, the loading position is exactly the calculation position of P for every thread. Okay? So I'm going to come back for a couple important reasons why we do things this way, and it will become very, very clear to you, what are the reasons why we drive this we use this design. But today, I want to make sure that at least you understand the basic concept of tiling, and also you understand how to write a piece of code for this particular usage. Okay, and then we come back and generalize into the coalescing and so on, why we want to do this kind of relative assignment. Yes? Question?
So what's the number of the tile width that will maximize the performance?
Okay, so what's the tile width that will maximize the performance? So that question will be answered very, very soon, because I'm going to go through some calculation and you'll see. It's actually slightly complicated, but not too complicated. So when we access the data from shared memory, remember, what we just talked about is how we're going to load each tile, right? We're going to load each tile into the shared memory. But once the shared memory, contains the tile, the inner product calculation is a little bit different than your basic matrix multiplication. The inner product calculation now access data from the shared variables, so the shared memory array. So they're going to be accessing subtile M and subtile N elements. So the way that you should think about it is that you're going to have a little subtile in the shared memory for M and the subtile in the shared memory for N. And then each thread is going to go down a small section of M and small section of N to produce the one phase worth, okay, of the inner product, right? So essentially, the Ty, okay, for M, the row index into the subtile M is going to be the Ty. Okay, the thread index Y will give you that row index. And then you use a index variable, a loop iterative variable K, essentially use a loop to walk down each of these elements. So we're going to see a for loop for every thread with an iteration variable K. And you're going to use this row, we're going to use that row variable to determine which Ty, we're going to use Ty to determine which row we'll be accessing, and then we're going to see the variable K used in the column index to go down the row. Here, for the column, we're going to do the same thing, but we're going to be using column, the COL variable, to, not the COL, the TX variable for the thread, TX variable for the column index, and then we're going to go down the row, so we're going to use K for the row index for the subtype of M. Before we go into the final code, we really need to understand what barrier synchronization means. In CUDA, a barrier synchronization in a thread block means that it's a statement. It's called sync threads. Okay, underscore sync threads, parentheses. And this is a statement. You're going to see that statement in the kernel. Whenever you see that statement in the kernel, all the threads have to reach that statement before any of the threads can continue from that statement. So let's say thread 1 executes and reach the sync threads. That thread is going to be waiting in that statement. The thread cannot escape from that statement. It cannot continue to execute any of the subsequent statements until all the other threads in the thread block have reached that statement. When everyone reaches that statement, then everyone will be released from the barrier, and they can all continue to execute the subsequent statements. Think about sync threads as a tour bus. Okay, when you go and let's say some of you probably have done this field trip with with this touring bus, right? So every time you let the kids out to a museum or something, you always tell the kids, come back, okay? Come back in 15 minutes or something, right? It never happens, okay? It never happens. They never come back in 15 minutes. They will be, so some of them will be back in 13 minutes. Some of them will come back in 14 minutes. Some of them may forgot to come back, okay? So the driver always does this, right? The driver or the tour guide always counts, okay? Always count and say, oh, I had 45 kids. And how come I'm only counting 44? Okay, that's the time you go out and find the last kid, right? So that's barrier synchronization. The whole bus, all the kids who came back 15 minutes or less are doing what? They're all waiting. They're all sitting on that bus waiting for the kid who forgot to come back, right? So that's barrier synchronization. You leave no one behind, and everyone waits for everyone else until everyone's on that bus, and then the bus moves, okay? So that's what barrier synchronization is. Yes?
So I can imagine that because you have lost so many active threads per block, so I can imagine you need to use a lot of blocks, but how do you actually estimate the loss of your the performance?
Okay, so the question is, how do you estimate the loss of performance because of barrier synchronization or because of these other things? The short answer is hard. These are the kind of things that are really, really hard to estimate. So, that's why sometimes you need to do experimentation. You just, these are the things that really, really hard to analytically determine, just by looking at it. So, the best use of this barrier synchronization is to enforce the discipline of tiled algorithms. So the discipline that we're going to enforce is that phase behavior, right? The phase behavior. So in every phase, we're going to use barrier synchronization to make sure that all the threads have completed loading the M and N elements into the shared memory. Because everyone is depending on that shared memory content, right? We're collaboratively loading the M and N elements into shared memory, right? And then we all consume the shared memory contents. So everyone depends on the integrity, okay, of the data in the shared memory. Everyone needs to use that shared memory. So we're going to use the barrier synchronization to make sure that all the threads have indeed completed loading their responsible M and N elements into the shared memory before anyone starts to consume the contents of the shared memory, right? That's obvious. You don't want anyone to proceed to calculate if someone is still loading the M or N element. You will be using garbage. So that's pretty clear. The second one is actually a little bit more subtle, and about half of the bugs in tiling code come from the second one. The second one is to ensure that all the elements in the shared memory have been consumed by all the threads before any of the threads will go ahead and load the next phase. The reason is when you go and load anything from the next phase or the next two tiles, you will be overwriting. You will be overwriting the shared memory location. So if any of the threads have not completed using the previous tile, and then you go and override that content, that thread is going to use incorrect data. The thread is going to be using data that's too new. You corrupted the input data before that thread was able to use it. So that's why the second point is to ensure that all the elements of the tile are consumed. In the restaurants, this is the part that the waiters and waitresses hate because that oftentimes reduces their tips. Their job is to clear up the dishes for you when you're done. But most of us are no longer trained to finish up our plate. Okay? When I grew up, my parents always tell me, finish your plate. Don't waste any food. But the health guidelines today tell people not to finish their plate. So you see these waiters and waitresses come in, and they have this fear on their face and say, are you done? And then, a lot of times there's still some food on the plate, so, we need to tell the waiter and waitresses, yeah, I'm done, or say, I'm still working on it, right? And it's a very awkward interaction, okay? And then all the waiters and waitresses dread that moment, okay? Then some people react violently. You're taking away my food, right? On the other hand, they're doing their job because they're doing that second barrier synchronization. They need to make sure that you indeed have consumed all the food that you want before they take away your plate, okay? And they don't want to take the plate away from you if you still want to take another bite. And that's the barrier synchronization, okay? The second one. Think about that when you write your code. So this is the mental picture that you need to keep for barrier synchronization. We have, threads executing, and some of the threads will reach the barrier synchronization earlier than others. So that's why the arrival time into the barrier synchronization can vary, dramatically sometimes across the threads. And then when the last thread, so thread n-2 reaches that synchronization point in this example, then all the threads can continue and be released from the barrier. So this is something that, going back to the question about the performance loss. So you can imagine that if we only have one thread block in the streaming multiprocessor, we're going to have fewer and fewer and fewer active threads as these threads wait for others on the barrier. In fact, in this example, during this time, when the second to the last arrival, there's only one active thread, right? Only one active thread in this example. So this is exactly the reason why we want to have multiple thread blocks assigned to each streaming multiprocessor, because we expect that some of the thread blocks will be executing barrier synchronization. So they may be, so they will have fewer and fewer threads active. But hopefully, other threads are not thread blocks are not executing barrier synchronization. They're at different execution stage of the same kernel, so that other threads can be still using the resources. One or two of those thread blocks are waiting on the barrier synchronization. Okay, so this is the reason why occupancy is very important. If you use know that you're going to have a good number of thread blocks in each streaming multiprocessor, then the effect, the negative effect or performance loss of barrier synchronization will be quite reduced. Okay, now, so let's take a look at this piece of code. This is the tile matrix multiplication code that you're going to write. And I encourage you to really understand this piece of code. Okay, after the lecture, go back. This is going to be one of those things that you really should spend some time, to chew on it, to really understand each piece of code, each part of the code, and then go and work on your MP3 from scratch. Okay, just logically think through. What are the parts that I'm going to write? Where are the barrier synchronizations? You do the whole thing just by thinking through it, rather than trying to copy this piece of code, because you will be amazed how much more you will understand this, by just doing that, and you will be also amazed how much you're going to forget to write into the code when you do this. Okay, and this piece of code only has about 16 lines. And we already know the first 2 lines, right? The first 2 lines I already showed you. That's a declaration of the shared memory, subtile arrays. So you said, hey, how can we use 2-dimensional notation for these arrays? Remember, these are static declarations. These are statically declared array with known sizes. The tile width is a compile time constant that you're going to change from 16 to 32 to 8 and do some experiments. But they are compile time constants. By the time the compiler gets its hand on this piece of code, the constant value is known to the compiler. So that's why the compiler can know exactly how much memory to allocate and how to calculate the linearized indexes for you. That's why for shared memory declaration that you use in the kernel, you can use 2-dimensional declaration, and also when you access these variables, you can use 2-dimensional indexing. Whereas M and N were CUDA-malloc. They are dynamically allocated according to the dynamic sizing. The compiler cannot figure out how to do the correct linearization calculation for you, so that's why you're going to be using linearized index for M and N. The next 2 lines of code are also extremely simple. We're just creating shorthand of thread idx.x and then thread idx.y and so on, because those are very long, so we're creating shorthand. This does not cost you anything at runtime. The compilers will automatically substitute the tx and ty with the thread idx.x and so on, during the compilation. So there's no overhead for this kind of stuff, but it makes your code a lot more readable. But it makes the expressions a lot shorter. So these are the shorthand that we often use for tile code. And the next 2 lines of code, 5 and 6, are exactly the same as the basic matrix multiplication code. We're still assigning every thread to calculate 1 p element, right? So we're calculating the row and column index for the p element that we'll be calculating. So back to that question, yes, we're still using the same output element assignment for every thread. So line 7 is still the same. We have, we're going to create a p-value. This is the p-value, the register. This is a register variable that's going to be accumulating all the inner product partial results until the end. Okay, so that's the p-value. So here is something that's a little bit different. Remember this m variable that I talked about? M is the phase. Okay, so we're going to be iterating using a for loop through the phases, phase 0, phase 1, phase 2. So m is going to give us the phase, okay, the phase. And for each phase, we start with phase 0 for all the thread blocks. At the beginning of the phase, we're going to load m and n elements, right, m and n elements into the subtile m and subtile n. Remember those slides that I show you for the index calculation? So this is the code that make every thread to go and load the m element and n element in the input tile in the same, what? In the same relative position as the p element that thread is calculating, right? If you happen to fall asleep during those several slides, go back and watch the video. There's a good reason why we record these videos. About 1/3 of you will be thinking about dinner or something when I talk about those slides. And then, you go back and watch the video and say, okay, so that's what he was talking about. That's fine, okay? I was a student. I know how it is, okay? Sitting in these lectures are hard, okay? It's much more fun to think about, what's going to be in dinner, what am I going to, to do for, lunch, and what? Oh, yeah. I'm going to, to call this recruiter, bump up my offer by 10K. Fine, this is great, okay? But occasionally you say, oh shoot, he was talking about something important. No problem. Go back and view the video, okay? So. So every thread, so this is a very, very important point here. Every thread is going to be loading one m and one n, right? So collectively, all the threads in the thread block will be loading one tile of m and one tile of n. So naturally, you expect a barrier synchronization right after these two statements, because you need to have a barrier synchronization to make sure that all the threads have completed loading the tile elements into the shared memory before what? Yeah, before anyone can consume, right? Anyone can calculate and consume the shared memory elements. Exactly right. So that's why you see this sync threads, okay? And then the next part is exactly the consumption part, the calculation part. So we're going to have a little for loop here with an iteration variable k, and the loop is going to iterate tile width times, because you need to take tile width steps in each phase, right? You're doing a small section of that inner product. In the inner product code, we're going to take one element from the shared memory array subtile m and one element from the subtile n, right? And do the multiplication, do the accumulation into that p-value. So this is literally where all the threads only access the shared memory and produce that little section of inner product. And p gets accumulated. So after this for loop, the thread is done with the current phase of calculation. But before this thread can move on to load the next m and n element into the shared memory, it has to wait until everyone else have completed consuming the shared memory. So that's why you do a sync thread right after that before you go back to the next phase. When you do the next phase, you'll be loading new m and n elements into shared memory, overriding, right? Overriding the what? The tile from the previous phase, right? Okay? So this is where the waiter or waitress is asking you, are you done with the food, right? Okay, yes?
Seems like Talent only has to reuse the data within the thread blocks, but there's like cross-thread blocks like reuse too.
Very good question. So the question is, it seems like by this design, we're only able to reuse the data in the shared memory within the same thread block. So multiple threads in the same thread block will be able to use the same element in the shared memory. Absolutely right. And the shared memory is per thread block. So that's why shared memory across thread blocks are different. So when another thread block try to use the same thing, it will not happen. So here, this is exactly, here is a very simple example. Let's say we have another thread block that's calculating this thread. Can you see this? Okay. So let's say here's another thread block that's calculating the output above the current block, right? So, the threads that calculating these P elements can also reuse the same data, right? But they cannot reuse that data because these threads in a separate thread block will be accessing a different shared memory. So they also have to load the same tile into their shared memory. So this limits the amount of reuse. This is the reason why for matrix multiplication, if you look at the real usage of each element here, let's say each element on this column, if you have 1,024 by 1,024, all these elements should be reused 1,024 times.
It's actually reduced by the tile size.
Yeah, so then the reuse is reduced to the tile size because of that limitation. So this is a real limitation. On the other hand, let me not go into to that one until a little bit later. There are other ways to use what we call the second level cache. So it actually mitigates a little bit of that. But this is a very, very fundamental limitation of these thread block-based shared memory approach.
So
Okay.
is there like a cross shared memory, like data transformation?
No, there's at least it's actually really complicated. My other hat is to work with some of the industry people to design these things, and that actually is extremely complicated. So nobody really wants to touch that design yet. Okay, so after all the phases are complete, then the thread has a complete inner product for the P element. So that's when P value will be written into row times, this is a linearized index of row and column, right? So this piece of code is complete. And every thread will go through this and with some spurious synchronization in the thread block. And this piece of code is only about 5 lines longer, okay, than the other piece of code. Yes? Okay, so the question is if the thread tile size needs to be the same size of block. The answer is actually no. If you look at the real tile code, the tile size is usually multiples of the thread block code for reasons of what we call the thread coarsening. And one of the reasons why we do thread coarsening is actually related to the number of reuse. Because if we fold multiple output, the tiles into the same thread block by using a bigger tile size, we can actually further increase the data reuse in the shared memory. So those are more advanced optimizations. So I think we're going to see one example in the machine learning example. Okay. Yes.
So I guess one of the questions I have is, why do we pick the tiles, I guess, to be subsections of the matrix as opposed to picking like our row column, like a row specifically to be the shared memory? Yeah.
So this is a very good question. The question is, how do we pick this design, right? How do we pick this design where the input tile and output tile are kind of the same shape, rather than trying to load, let's say, an entire row or entire column into the shared memory? So you can actually do that. Okay, you can actually change. This is what I mean by rectangular tiling. you can actually design your tile to be rectangular. You can have, somewhat, shorter but wider tile. And then you can keep pushing it until it becomes one row, right? It is entirely possible. And, you should actually experiment with that. It's a lot more complicated than this. So, it will take more than one lecture. So I'll let you do it rather than me. This is great. Experiment with as many of these things as possible. Okay, we're almost there. So you have seen the code, so you can start doing the matrix multiplication. And if you compare that code with the basic matrix multiplication code, there are only about 5 lines of differences. So this is actually one thing important to remember. When you do high-performance programming and parallel programming, oftentimes the elements or the essence of the techniques don't take a large number of lines of code to write. It's not like Java programming where you may be writing 2,000 lines of code every day, okay? You might be only writing 5, 6 lines of code a day, but these things actually need to go through a very engineering kind of process in the design. The design of your code is a lot more than the actual lines of code. Okay? Oftentimes, the explanation of 5 lines of code can take literally tens of pages to explain this. Okay? Do yourself a favor by writing down all the design, the decisions and so on for that piece of code, because in a month, you're not going to remember. Okay? So here's a quick calculation, and we're going to be done right after this. So for the shared memory size, for Maxwell is 64K bytes. So we can pick 2 different tile sizes or many, many more. So I'm going to use 16 versus 32. Okay? So for 16, each thread block will use 16 by 16, which is 256 elements for M, and 256 elements for N, so that's 2 times 256. And each element has 4 bytes. So this means that the input tiles for each thread block will take 2K bytes for both M and N. And then shared memory can potentially support up to 32 active thread blocks, because 64K divided by 2K is 32. So that's great. We can take 32 thread blocks. And the threads per SM constraint is 2048. So we have 256 threads per thread block. So we can, we can easily have up to 8 thread blocks. 2048 divided by 256, that's 8. So it's within the limit. And this allows up to 8 times 512, which is 4,096 pending loads. Every thread will have 2 loads. And then you can produce 256 times 2 times the number of thread blocks that you need to, you can accommodate within each thread SM. Now, if you use thread tile size of 32, you go through the same calculation. Each thread block will now use a lot more shared memory, a lot more. So that will take 8K bytes. But 8K bytes is still comfortably going to fit 8 thread blocks in the streaming multiprocessor, because we can take up to 64K bytes of shared memory usage. So as far as the number of threads and the number of active loads, they are actually equivalent, right? For 16 by 16 and 32 by 32. So which one would you pick? You will pick 32 by 32 in this case. Because for 32 by 32, we reuse the data 32 times rather than 16 times. So we cut down the number of global memory accesses by 2 times more. Okay? So if we use 32 by 32, we actually can use 158 gigabyte per second bandwidth to support 150 divided by 4, but now we reuse the data 32 times. So we magnify that bandwidth by 32 times, and so now we can support 1.2 teraflops. And that's exactly what we need. We can actually improve the execution to almost 100% of our peak performance. Okay? So do MP. So this is, well, I'm going to start from this next time. you have everything you need to start MP3. Okay?